Okay, this will be the AP exam review for Chapter 15, the chapter of equilibrium. Very important chapter. So let's get to it. Question 1 says, when 4 moles each of X and Y are placed in a 1-liter vessel and allowed to react to reach equilibrium at constant temperature according to the equation above. Notice we have X plus Y in equilibrium with 2Z, a general version of an equation. 6 moles of Z is produced. What is the value of the equilibrium constant Kc? Remember, Kc is products over reactants at equilibrium. So what we recognize is that we have initial concentrations. So this 4 moles means how much was put in at the beginning. And then this is the number that we got at equilibrium. So we have to set up the icebox. In fact, let's do it like this. Let's set up the icebox right below, so it's a little easier to see. And the idea here is we begin with 4 moles each of X and Y, which means this is 4, and we assume we have nothing of Z. In the initial step, in the I, you can always, unless they say to you that there's something of Z in the flask, you can usually assume it's 0. Now, it says that at equilibrium we find 6 moles of Z. That's this E, so we have 6 here. And as we get to equilibrium, we must have lost some of our reactant. We must have gained product. We know that because we end up with a bunch of product where we had none at the beginning. And the question is how much? Well, it looks like we've added 6 moles of Z, going from the initial to the equilibrium, which means we've lost an amount of the reactants. Now the stoichiometry tells us that for every 2Z we gain, we lose 1Y, 1X, because these are 1s, which means we lost 3 here, we lost 3 here. Combining the initial and the change, we have 1 and 1 left at equilibrium. If we want the equilibrium constant, for this specific case, we've got Z, the concentration of Z squared, because of this 2 coefficient, divided by the concentration of X, multiplied by the concentration of Y. And so let's plug this in. So we have 6 squared, essentially, over 1 times 1, because 6 is the product and these are the reactants, which gives us 6 squared, which gives us 36, and that is the answer. So notice this is a quick little icebox showing up on a multiple choice question, which these are out there. So be aware and be careful. Okay, how about we try the next one? The next one actually is a 4-part question. So let's see if we could see what they are talking about, and then we'll, or the next 3 questions, I think, ask about the same concept. So, the next 4 questions. Here we go. We have an equation here, PCl5 breaking down into PCl3 and Cl2. And that's what they tell us. PCl5 decomposes into these 2 compounds and an element. According to the equation above, a pure sample of PCl5 is placed in a rigid evacuated 1-liter container. So here's what we have. We have a container with PCl5. The initial pressure is 1 atmosphere. That's why we say 1 atmosphere. The temperature is held constant until the PCl5 reaches equilibrium with its decomposition products. The figures on the right show the initial equilibrium conditions. So at equilibrium, so this is initial, and this is equilibrium. At equilibrium, we see that we have all 3 of these in the vessel, which makes sense because the reactions don't really go to completion. They reach equilibrium, in which you have everything. You have a little bit of this, you have a little bit of that. And we see that total pressure is now 1.4. So hopefully we see the picture here. The first question asks, which of the following is most likely the cause for the increase in pressure observed in the container as the reaction reaches equilibrium? So, some of our options are a decrease in the strength of the intermolecular attractions among the molecules in the flask. Now, the intermolecular attractions represent, remember, if you have intermolecular attractions, that means the substance is a liquid. It means the molecules are attracted to each other, and because they're attracted, they form into a liquid or into a solid. So intermolecular forces have nothing to do here because we have gases and we're not forming any liquid. Molecules are not coming together. So in fact, both of these questions are out. A and B are out because intermolecular forces don't play a role with gases, is the idea. C says an increase in the number of molecules, which increase the frequency of collision with the walls of the container. This one is correct. Since we have our pressure increase, that means there are more molecules in here pressing against the container. And we have more molecules because we've lost reactant and gained product. We actually gained more product. That's why C is the correct answer, because our pressure has increased. Incidentally, D is incorrect. An increase in the speed of the molecules. Speed of molecules would increase if the temperature increases, and we were told that the temperature is held constant. Okay, hopefully this one makes sense. How about the next one? Next one says if the decomposition reaction were to go to completion, the total pressure in the container would be. So here we have our reaction. Let me just recopy it here so for ease of viewing. PCl3 and Cl2. And we're asked what would the total pressure be. Well, since we begin with 1, let's think of our icebox again. This is actually good to think of the icebox in this case. It's always a good idea to think of an icebox. Since we begin with 1 and nothing of 0, if we were to completely react this one, which means we would lose 1 here, add 1 here, and add 1 here, we'd have 0 for our equilibrium, and we'd have 1 and 1. Now, equilibrium systems don't go to completion. That's kind of the definition. But if it were to go to completion, then you'd have twice as much pressure as you initially started, because every PCl5 would have decomposed into a PCl3 and a Cl2. So in fact, you have a total of 1 plus 1, 2 ATM. And that's as simple as that. Not bad? 4 says, which of the following statements about Kp, the equilibrium constant for the reaction, is correct? And we have really 3 choices, or 4 choices. Kp is greater than 1, less than 1, equal to 1, and sorry, we can't determine without additional information. Now, remember that we said if Kp is a high number, which means like above 1, that means we have a lot of products at equilibrium and a little bit of reactants. That would make, because K, recall, is products over reactants, that would make a big number on top, a small number on the bottom. The reverse is true. If we have a lot of reactants, a little bit of products, K would be a small number, because you have a small number on top and a big number on the bottom. And if K is 1, that means roughly you have equal amounts. Now, this also is dependent on the type of reaction you have. So, in other words, if you have a lot of products and only 1 reactant, then the products have a bigger effect, you can say. Okay, so if you were to choose as a guess, do you think at this equilibrium, do you think we have more products or more reactants? Now, if you said more reactants, you are correct. In fact, the picture that I drew is roughly correct. At equilibrium, we have a little more products and a little less reactants. We know that because the total pressure went up, but not by that much. We know we didn't completely get rid of the reactants, but we formed a little bit of the products. That's why the total pressure went up by a little bit. So knowing that the total pressure went up by a little bit, we have a little bit of our products and still quite a bit of reactants left, which means our number on top is smaller, so 0.4 or something. The number on the bottom then is still bigger, and because we're squaring the top, 0.4 squared, this will give you a smaller number still, like 0.016, something like that, or actually 0.16, wouldn't it? Right, 0.16. And so the whole point is Kp is less than 1 because you have less products, more reactants. If this one's a bit confusing, you can actually work it out. It's possible to work this out using the icebox. And the way you would do it is you would use x's instead of 1s. You'd say minus x here, you'd say plus x, and this becomes x, this becomes x, this would become 1 minus x. And you can actually solve for the total pressure, because these are all gases. Total pressure, which is 1.40, will equal 1 minus x plus x plus x. All of these combined together. And then you can solve for x, and you'll see that we indeed have a small number. These are small numbers, and if you plug it in for the k, you'll find out it's less than 1. In this case, they wanted you to kind of guess, or guesstimate, I should say. But there it is. Let's go ahead and do the next one that still is asking about the same equation, this last one. And number 5 says additional Cl2 is injected into the system at equilibrium. Which of the following graphs best shows the rate of the reverse reaction as a function of time? Assume that the time for the injection is negligible. Okay, so we have 4 possibilities. We see that Cl2 is added and the rate goes up. Cl2 is added, rate goes down. Cl2 added, rate goes down, rate goes up. So, first of all, the reverse rate, remember that at equilibrium, the reactants and the products are in equilibrium because the forward rate is equal to the reverse rate. So the rates are equal, which means that the reverse rate going this way is a non-zero number. It means it's a number above 0. Oh, and this one is wrong because it shows the rate to be 0. The rate will not be 0 at equilibrium. The rate is some value, 0.4 or whatever it is, but it is not 0. So we have these 3 choices. Now choice D is out because as soon as we add the Cl2, because you increase the concentration, the rate increases right away, and then as the product, the increase in the product is taken to the left, the rate decreases. So you actually won't see an increase, you'll see a sudden increase and then a gradual decrease. So this one's wrong because this shows a gradual increase. The 2 pictures that are possible are these 2 pictures, where there's a sudden increase in Cl2 and you have a sudden increase in the rate, because rate increases as you increase the concentration from chapter 14, if you remember. The question is, as the rate decreases, will it level out above or will it level out below the initial rate? Well, because we've added more product to the system will try to remove that product, but it will not be able to remove all of it, which means we will have more product left, and the rate will actually increase. So this one shows the initial rate lower, the final rate higher. This one shows the initial rate higher, final rate lower. It shows the rate going down. This one shows the rate going up. The rate will go up because eventually you've added more product and the system will shift to the left to remove the product. This is Le Chatelier's principle, but it will not be able to remove all the product. And that's why B is the best answer. Okay, so let's do the last one here, number 6, which shouldn't be too bad. Here we're asked about the synthesis of CH3OH from CO2 and H2. So you see the reaction here. Represented by the equation above, the value of Kc for the reaction is, at this temperature, is 14.5. Which of the following explains the effect on the equilibrium constant when the temperature of the system increases to 650 K? The temperature goes up. Now we'll notice that the reaction is delta H is less than 0, which is, say, delta H is negative, which means it's exothermic, recall. This is going to be our clue. So we're asked what happens to the equilibrium constant. Again, remember that the equilibrium constant is products over reactants. Now, equilibrium constant is actually temperature dependent. These constants, as all constants, are temperature dependent, which means they change as temperature changes. So D is actually out right away. Kc is a constant and will not change. It's true it's a constant, but temperature will affect it. So it will change based on temperature. So A says Kc will increase because the activation energy of the forward reaction increases more than that of the reverse reaction. Well, activation energy here is really not a factor. B says, let's think about all these and then pick one that works best. Kc will increase because there are more reactant molecules than product molecules. This is true, but that won't change Kc. Now this one says Kc will decrease because the reaction is exothermic. Let's think about this one. The reaction is exothermic, and as we're increasing the temperature, notice we've increased the temperature, effectively, because reaction is exothermic, we can think of heat as a product. We're increasing the temp, so we're adding heat to the system. The reaction switches to the left to remove that heat. So what it does is it decreases the amount of products and increases the amount of reactants. The reactants increase, the products decrease. The top number goes down, the bottom number goes up. So this is actually the best answer. Kc will decrease because the reaction is exothermic. The rest of the questions, the concentration actually doesn't change Kc, and activation energy is more to do with rates, doesn't really change Kc. Okay, I know these were tough questions. Go ahead and think through them and get ready for the test to answer similar questions mañana.